Welcome to this lecture on transition metal organometallic chemistry from principles to applications. In our previous lecture, we have been dwelling upon a very interesting topic on transition metal perfluoroalkyl sigma complexes. These complexes are designated by the type as shown here, and they are involved in some kind of sigma interaction with the transition metals. These complexes we have discussed show extra stability as compared to the corresponding transition metal sigma alkyl complexes, more stable as compared to transition metal sigma alkyl complexes, which are designated by RH sigma Tm. Also, what we saw is that these complexes show different reactivity as a result of reversal of polarity with regard to this transition metal sigma alkyl complexes. So, because of this reversal of polarity, the reactions which would happen naturally for transition metal sigma alkyl complexes does not occur or go the opposite way for transition metal perfluoroalkyl complexes. So, that leads to a very interesting complementary comparison between these two types of complexes, which are both of sigma types, but they show very different reactivity and property as well as their stability. So, with that we have looked into various methods available for preparation of these transition metal perfluoroalkyl complexes, and one or two methods that we have discussed involved replacing a fluoride anion with a metalate anion, and in the process making these transition metal perfluoroalkyl complexes. So, in this lecture we are going to discuss some more interesting synthetic routes for preparation of these transition metal perfluoroalkyl sigma complexes. The first and the most common one is the method of oxidative addition. Perfluoroalkyl iodide can be oxidatively added against a low valent metal center, for example, iron pentacarbonyl, giving the oxidatively added product plus CO. So, here the iron is in 0 oxidation state and it is a 18 valence electron compound. After oxidative addition, as expected, the iron is in +2 oxidation state and it is also a 18 valence electron compound. Actually, it loses as CO to become coordinatively unsaturated to give 16 valence electron compounds, which then oxidatively add to give the resulting CO4 Fe RFI 18 valence electron compound. As discussed in our earlier lecture, that the there is a reversal of polarity in this RF bond, and that RF side is carbanionic, whereas iodide side is carbocationic. This is very different from any alkyl iodide, where the iodide side would be negatively charged and the carbon side would be cationic in nature. So, we see that there is a reversal of polarity for these perfluoroalkyl type of compounds, and that have been used successfully in preparing these perfluoroalkyl transition metal sigma alkyl complexes through this method of oxidative addition. Another method that exists is called oxidative cycloaddition. And this involves addition of an olefin of perfluoroalkyl compound, resulting in a metallocycle of the type shown. So, here too is this low valent iron center reacting with 2 molecules of C2F4 perfluoroethylene, giving this 5 membered metallocycle. Here the oxidation state of iron is in +2, and it also has 18 valence electron, whereas in the starting precursor iron is in low valent 0 oxidation state and having a 18 valence electron configuration. Now, in the process of oxidative addition, the iron initially, like in the previous example, releases a CO to become coordinatively unsaturated, which then undergoes this oxidative cycloaddition with 2 molecules of C2H4, resulting in this perfluoroalkyl cycloalkyl iron compound as shown over here. So, these two oxidative addition reactions are kind of related in terms of the fact that the iron center increases its oxidation state by +2, and one involves just the oxidative addition of an perfluorohalide, alkyl halide, and in the other case it is a perfluoroalkene, 2 molecule of these reacting to give the compound. Another interesting reaction involves insertion of this perfluoroalkene into metal-metal bonds. And this is given by the reaction C cobalt dicobalt octocarbonyl reacting with perfluoroethylene giving CO4 cobalt CF2 cobalt CO4. So, here is similar to any other insertion reaction of the corresponding alkene, where the alkene insertion into a metal metal bond has occurred, and the similar path strategy has been successfully employed in preparing this perfluoroalkyl bimetallic cobalt compound as shown over here. Now, we had looked at various kinds of activation reactions, particularly from the utility point of view. We started with CH activation and saw that CH activation was an important reaction leading to various functionalization products which would produce value added chemicals from simple hydrocarbons. And what we saw is that CH activation was quite challenging as a result of very high CH bond energy. The bond was very difficult to break, and the CH bond energy was around 410 kilojoule per mole, and the challenge as mentioned for CH bond activation had been because of high bond energy plus to achieve selectivity. So, what we saw that CH bond activation was quite challenging, primarily because of its high bond energy as well as of its very high ubiquitous nature, that selectivity becomes the issue. Following that, we have looked into CC bond activation, and what we found that CC bond is even more difficult to activate, despite the fact that CC bond is somewhat easier to cleave. CC bond energy is around 350 kilojoules per mole as opposed to 410, but CC bond activation is more challenging. Because of steric unapproachability, leading to the pre-coordination complex required for initiating the activation reaction becomes even more difficult. So, what we saw that even though the CC bond energy was slightly lower than that of CH bond energy, its activation was even more challenging because these bonds are deeply buried, they are outnumbered by CH bonds. As a result, the pre-coordination complex required for initiating the activation reaction becomes even more difficult, and CC bond activations thus becomes more challenging than CH bond activation. And what we saw that the examples which had CC bond activation had to do with release of ring strain in the substrate resulting in CC bond activation, and hence it is more difficult. Now, when this in the context of these two, when we look at CF bond activation, it becomes all the more challenging, primarily because CF bond energy is the strongest, and it is way higher than C and CH, and it can vary between 400 to 500 kilojoule per mole, and that is extremely high as compared to CC and CH, which makes CF bond activation very extremely challenging. So, this sort of gives a overall picture that if one goes down the group CH to CC to CF, difficulty in bond activation increases as one goes down the group, and that primarily for CF is due to the very high CF bond energy, which lies between 450 to 500 kilojoules per mole, and are way higher than that of CH, CC and CH bond energies as shown over here. Now, that being the fact that CF bonds are difficult to activate, there are very many strategies in place which facilitate CF bond activations. These are very clever approaches which circumvents this barrier of very high CF bond energy that makes the CF activation very difficult. And one such strategy that is in place is achieving CF bond activation by electron transfer pathway. This is illustrated in the following example. For example, for this perfluoroalkyl compound RFCF3, to which an electron is added to produce this radical anion, this is a radical anion and hence unstable, and it releases a fluoride anion to give RFCF2 dot radical and an anion F minus. So, in the process what one sees that the CF bond in this RFCF3 has been cleaved to CF2 and F. So, that is how the activation has been achieved, and activation has been achieved by addition of an electron resulting in the formation of an unstable radical anion, and the radical anion stabilizes itself by decomposing from its radical anion state to give a radical species and anionic species as shown here, thereby achieving this CF bond activation. So, So, apart from supply of electron, sometimes organometallic species also helps achieve CF activation through coordination. I will illustrate this with an example. Electron poor or electron deficient organometallic species forms CF M coordination to facilitate CF activation, and this is illustrated by this scandium complex Cp star 2 scandium hydride reacting with this olefin HFC H2 to give this compound. Cp star 2 scandium interacting with fluorine of this alkene that finally results in the formation of Cp star 2 scandium fluoride and ethylene. Here too what one observes is that this fluorine is sort of abstracted by this electron deficient species scandium and interchanged with the hydrogen which scandium had, leading to this CF bond activation. So, reviewing the methods available for activating CF bond, what one sees that the successful strategy involves either donation of electron resulting in an unstable radical anion species which thereby stabilizes by undergoing CF bond activation, or by achieving CF bond activation by coordination with electron deficient transition metals, and this can be also achieved by increased reactivity of transition metal perfluoroalkyl moiety. For example, in this example CF activation achieved by increased reactivity of transition metal RF moiety. This is an interesting example in which Cp star tricarbonyl molybdenum CF3 compound, when treated with Me3SiO2 CF3 eliminates the Me3SiF molecule which abstracts this fluorine from one of the CF3 molecule by the silicon cation that is coming from Me3SiO moiety, and that results in this interesting Cp star tricarbonyl molybdenum CF2 difluorocarbene complex with this SO3 CF3 minus anion, and this anion is derived from this part of the reagent. Now, this is a very interesting reaction whereby by using TMS triplet one can abstract the fluoride from a transition metal perfluoroalkyl residue, giving rise to CH activation. The driving force for this reaction is twofold. First, from the formation of strong MoCF2 moiety, where you see a double bond of MoCF2 formed, and second thing is formation of strong SiF bond, which is in this. So, with this I would like to review what we have discussed in today's lecture. We have looked into various synthetic protocols available for preparing transition metal perfluoroalkyl complexes, which mainly include oxidative addition reactions and oxidative cyclization reactions. We have also looked at CF activation in the perspective of CH and CC activations. Owing to very high bond energy of CF bonds, which can vary from 450 to 500 kilojoules per mole and are by far more higher energy than that of the bond energies of CH and CC bonds, CF bond activations are extremely challenging to achieve. However, we have also seen that few successful strategies that are put in place to achieve CF bond activation, which involved electron transfer pathway resulting in anion radical, which led to CF bond activation. We have also seen coordination or fluoride abstraction with electron deficient transition metal complexes resulting in CF bond activation, and lastly in this example we have seen that CF activation by increased reactivity of transition metal perfluoroalkyl complexes. With this I conclude today's lecture and look forward to being with you in the next lecture, where we are going to discuss some more reactivity pattern of CF bond activation reactions and that of perfluoroalkyl transition metal complexes. Till then, goodbye and see you in the next lecture. Thank you.